Welcome to the Explainer. Today, we are pulling back the curtain on C++ to look at how it manages its most fundamental unit, the object. This is a core concept that every developer really needs to get a handle on.
So let's start with a question that gets right to the heart of things. Have you ever really stopped to think about it? When you write a simple line of C++ code to create an object, what is actually going on under the hood? I mean, where does this thing live in your computer's memory? And more importantly, how long does it stick around?
You see, to really get a grip on C++, you have to think of every single object as having its own little life story. It has a beginning, a middle, and an end. It's born, it does its job, and then, poof, it's gone.
Now, for most objects, this life is pretty short. They pop into existence when a function starts, and they're usually stored in a super fast temporary memory spot called the stack. Think of a stack of plates. Last one on is the first one off. When your function ends, its plate is taken off the stack, and the object just vanishes. This automatic cleanup is super convenient, but it also creates a challenge. What happens when you need an object to stick around?
And that's the big question, isn't it? How do we get around that limitation? Well, this leads us to one of the most powerful features in C++, the ability to manage memory directly. This is how we give objects a life that goes way beyond the function that created them.
This whole process is called dynamic memory allocation. It's kind of like asking the operating system for a plot of land to build an object on. You, the programmer, use the new operator to say, hey, I need a spot. And then crucially, you decide when to tear it all down with the delete operator. This gives you precise, total control over an object's lifespan. Now, if you've ever worked with C, you might be thinking, wait a minute, C has malloc for this, and you're absolutely right. But C++ took that idea and made it so much better. See, malloc is, well, it's a bit primitive. It just carves out a raw chunk of memory and hands it to you. The new operator in C++ is way smarter. It doesn't just allocate the memory, it also calls the object's constructor, which is what properly brings it to life. Plus, it's type-safe, which saves you from a whole world of bugs. And this diagram just makes it all crystal clear. On the left, you've got the stack. That's for your fast temporary variables that clean themselves up. But when you use new, the object itself is created over here on the right in this big flexible memory pool called the heap. And that variable you have on the stack, it's not the object anymore. It's just a pointer, basically an address that says, hey, the real object you're looking for is over there.
And this is super important. It's the classic with great power comes great responsibility. If you use new, you must use delete. If you allocate an array with new square brackets, you have to free it with delete square brackets. If you forget, you create a memory leak, where your program just keeps eating up memory. Even worse, if you try to use a pointer after you've deleted what it points to, you get a dangling pointer. And trust me, that's a one-way ticket to a crash.
Okay, so that's how we manage the lives of individual objects. Pretty cool, right? But let's shift gears a bit. What if you have a piece of data that belongs to an entire class, not just a single object? Think about it for a second. Imagine you want to count how many player objects are currently active in your game. If you put a counter variable inside each player object, every single player would have their own personal count of 1. That's not very helpful. You need a single shared counter for all of them. So where do you put it?
And this is where the static keyword comes to the rescue. This is the perfect analogy. A normal member variable is like a personal diary. Every object gets its own private copy. But a static member is like a shared bulletin board. There's only one for the entire class, and every single object can see it and modify that same exact copy.
Let's look at a quick example. See this count variable? It's marked static. That's the magic word. It means this variable doesn't live inside any one instance counter object. So every time a new object gets created, its constructor increments that one shared count. Oh, and you'll also notice that line at the bottom. You have to define and initialize the static variable outside the class. That's what actually sets aside the memory for it. This table really hammers home the difference. A non-static variable, an instance variable, that defines an object's unique state, it's like its personal DNA. A static variable, a class-level one, defines a property of the class itself. And understanding this distinction isn't just a technical detail, it's absolutely fundamental to good object-oriented design. And it's not just for data. Functions can be static too. A static function isn't called on a specific object, it's called on the class itself. Think of it as a utility function that's related to the class as a whole, but doesn't depend on the state of any single object. That's exactly why it can only access other static members. So, let's zoom out. Why do all these features even exist? Why this complexity with new, delete, and static? Well, they aren't just clever tricks. They are the essential building blocks for a much, much larger design philosophy.
This right here connects the how of C++ syntax to the why of software architecture. Mastering these low-level tools is what lets you build robust, flexible, and maintainable systems, which is really the whole point of object-oriented programming in the first place.
And these are the big goals, the 4 major pillars of OOP. We want to simplify complexity with abstraction, protect our data with encapsulation, make our code reusable through modularity, and organize everything logically with hierarchy. They all work together to help us write better software.
This slide is a great example of that hierarchy pillar. Now, hierarchy isn't just about inheritance, where a poodle is a type of dog. It's also about composition, where one object has another object as part of its state. Here, an employee object contains a date object. It's like building with Legos. You build complex systems from smaller, simpler, reusable parts.
All right, we've covered a lot of ground. So let's wrap this all up with a really practical tip you can start using right away to write better, more effective C++ code.
This is a fantastic rule of thumb. You see, inside every non-static member function, there's a special hidden pointer called this. It's how the function knows which specific object it was called on. So if you're writing a function and you realize it doesn't need to access any of an object's unique data, if it doesn't need the this pointer, then it should probably be static. It's a really clear signal to other developers about what that function is for.
So if you remember anything, remember this. Use new and delete for objects that need a flexible lifespan. Use static for data and functions that need to be shared by all objects of a class. And finally, mastering these tools isn't just about syntax. It's about learning how to build powerful, well-structured designs.
So there you have it. The secret life of objects isn't so secret anymore. Now it's your turn to apply these concepts and take your C++ skills to the next level. Thanks for joining this explainer. Go out there and build some smarter objects.